I am going to actually sort of revise or reprise a talk that I gave at the American Museum of Natural History a couple of years ago before COVID, but it's still relevant. And I love Venus, and I hope at the end of this talk you'll understand why. so um, so I'm just going to get started, and I like to start talking about habitability with this image, because this is an image of the a little tiny, if you were to look at the sky and just pick out like a period, the size of the sky that's the size of a period on a sentence, this is what is in that little piece of sky. So everything you're seeing here is actually a galaxy. There are a couple of stars here. Here's one, here's the star, a couple of the little bright things, but all of these fuzzy patches are galaxies. And this is an image taken by the Hubble Space Telescope, where it just stared at the sky for a little while and to see what it could see. And I like this picture because it shows us that there are trillions of galaxies, and in those galaxies, there's trillions of stars. And now we understand that around almost every star in the galaxy are planets. So planets are ubiquitous. And despite all of these trillions of planets and stars and galaxies, to date, the only evidence we have that our universe is inhabited is us. We are so far, to our understanding, the sole representation of life in the universe. And I hope that we see that that we learn more if that is indeed the case. So we live in a very habitable solar system. And so if we look at the planets in the solar system, the inner planets, what's shown here are the inner planets: Mercury, Venus, Earth, Mars. And then the large planets are not here, but several of their moons are. And if we look throughout our solar system, there are many habitable worlds in our own solar system. So obviously the Earth is habitable. And as we, oh, my little button is not working. And what I will, so Earth is habitable today. And the question is, what do we know about the other planets to assess whether they are habitable today or whether they were habitable in their past? And to understand that, we have to understand the keys to habitability. So this is a video taken from the International Space Station. What I like about this picture, so here's the Atlantic Ocean. And one of the things that shows up beautifully in this image of our own gorgeous planet is so this is Africa, this is the Canary Islands, this is the Atlas Mountains, and then we're going to end up in Spain. Okay. So one of the things that makes our planet habitable is our wonderful atmosphere. And this atmosphere protects us from space, and it keeps our temperatures within the range that allows liquid water to exist on the surface of the planet. And for life as we know it, that liquid water is essential to life. So the presence of our atmosphere and the gases in the atmosphere are a sign of habitability, and in particular, the presence of liquid water. And if we look at other solar systems, we can define a zone around any star that is the zone at which the temperature should be such that liquid water will be stable. And this is called the habitable zone. And if we look at our own solar system, Mercury, Venus, Earth, and Mars, the Earth is right in the middle of the distance where the temperatures are hot enough to keep water liquid. But you'll notice that both Mars and Venus are in sort of the edges of the habitable zone today. And I'm going to argue that they may have been in the habitable zone in the past. The other thing about planets that lets us understand their habitability is shown in this picture. So this is another picture of a volcano erupting on the Kamchatka Peninsula. So this is a volcano. It's in Russia, but it's in the part of Russia that is north of Japan. And this is again taken by an astronaut aboard the space station. So I love this picture because the astronaut's just looking out the window and there's a volcano erupting and the astronaut's like, oh, I'm going to take a picture. But I like this picture because as a geologist, this reminds me that when volcanoes erupt, they release a lot of ash and dust, but they also release a lot of vapor and water. And what you're seeing here is a cloud, a water cloud, that is produced as the water that comes out of this volcano reaches the colder parts of the atmosphere and condenses into a cloud. Now on Earth, we have so much water that it's like, who cares if volcanoes erupt water? But this process is incredibly important to maintaining our water-rich atmosphere because volcanoes are the way that gases and water get from the interior of the planet to the atmosphere. The water cycle depends on active volcanoes to bring those gases from the interior of the Earth to the exterior of the Earth. So volcanic activity is really important to maintaining an atmosphere. And to have volcanic activity, you need to be hot. So the Earth, this is just a picture of how the Earth convects. This is the core of the Earth, and cold things go down and hot things come up. But this convection drives volcanism on the Earth. And so so when we look at other planets and we want to understand if they're habitable, one of the main questions we have is that planet volcanically active? And what we found is it's a really simple thing, actually, that the larger you are, the warmer as a planet, the warmer you are. So habitable planets must be large enough to stay geologically active for a long enough time that life can develop. And if we look at the sizes of the planet, all planets start out hot, but the small planets cool off really fast. So when I talk to my students, I talk about the difference between peas and potatoes, right? Like you're having Thanksgiving dinner and you've got a pea and you've got a baked potato, and the pea cools off really fast, but the potato takes forever to cool off, right? Because it's larger. And it's the same for planets. All planets start off hot, but the little peas like the moon and Mercury cool off very quickly and their volcanism shuts off. But larger planets like Earth, which is volcanically active, as we know, and Venus, which is the same size, should both have geologic activity to drive volcanism and drive a water cycle in the planet. So Mercury and the moon are too cold. We have geologic activity on Earth. We think we had geologic activity on Mars. And the prediction about Venus, just based on its size, is that it should be a planet that has active volcanism. The other effect of a planet's size is the ability to hold on to an atmosphere. So an atmosphere is held on to a planet by the planet's gravity, and small planets like the moon and Mercury are too small they don't have enough gravity to hold on to an atmosphere. So they're atmosphereless bodies. Mars is a little bit larger, so it has a little thin atmosphere, but Earth is large enough to hold on to an atmosphere that we describe, the pressure we feel is 1 bar. Mars has a very thin atmosphere because it's smaller, and Venus has a massive atmosphere today because of its size. So of all the planets in the inner solar system,
we have two planets that should be geologically active today and can maintain atmospheres. Both factors are essential to life, and this is Earth and Venus. So when we look back in time at the solar system, I'm going to try to convince you that we have many planets in the solar system that may be habitable in the past and even today. Earth, Europa, which is a moon of Jupiter, Titan, which is a moon of Saturn, Enceladus, another moon of Saturn, Mars, which was habitable early in its history before it cooled off. And then the question is whether Venus was habitable at any point in its history. And what I'm going to try to argue is that Venus was, if you were an alien and you came to the solar system when it was young, you would have found 3 bodies in the inner solar system, 3 planets, all of which had oceans. This would be Earth, Mars, and Venus. And at least on one of them, life had already developed. So our understanding of life predicts that both Venus and Mars may have been habitable early on. And so we should consider both planets as potential places where life may have evolved early. So we want to know if Venus was habitable, and to understand that, we need to look at the history of water and geologic activity. This is a picture of Venus taken by a spacecraft that's in orbit today, the Akatsuki spacecraft, with its beautiful cloud deck. And Venus, of course, is the brightest object in the sky. This is not today, this was 2 years ago, but Venus is the brightest object after the sun and the moon. And so when Venus is up, you certainly can see it. And as such, there are a lot of people who Venus figured very prominently in the culture of the Mayan civilization. This is an observatory built to look at Venus. And the Venus was also a really important target for Galileo to understand how the planets were arranged in the solar system, in that Venus goes through phases like the moon. And it does this because it is a planet that is interior to the Earth. So the sun and the Earth, and as Venus orbits the sun, sometimes we see it as a full planet, sort of a full moon, and other times we only see a crescent. And this helps solidify, Galileo's observations in the 1600s helped solidify the position of Venus as a planet that was closer to the sun than the Earth. Okay, so Venus, this is what Venus would look like if you're floating above Venus with your eyeballs. I mean, just with your naked eye. And it is the reason why it's so bright is because it has a really thick cloud cover. And this cloud cover reflects most of the light back to your eye. And so it has this very bright color. And what we understand from the Mariner mission in the 70s is that the atmosphere is 95% carbon dioxide, and this carbon dioxide atmosphere, because of the greenhouse effect, results in a very high temperature surface and a very high pressure surface. So the surface temperature is 450 degrees Celsius. So liquid water is not stable on the surface today. And the pressure is about 90 times what you're feeling right now. So the thickness of the Venus atmosphere is actually kind of like being underwater in terms of the viscosity and the heft of the Venus atmosphere when we're at the surface. But even though that's very daunting, the first planet we ever landed on as humans ever was Venus. And so the Soviets decided in the 60s that they were going to try to go to Venus, and without any information about the surface, like they had no images. They're just like, we're gonna. So they designed the spacecraft called Venera. That's basically a thermos bottle with instruments inside and a big tire on the bottom. And the Venera spacecraft were the first human-made spacecraft to enter the atmosphere of another planet in 1967, to land on a planet in 1970, and to return images from a planet in 1975. And this is what it looks like.
this is what it looks like. So these are two of the image of the landers, and we can see rocks, which is what you expect on the surface of the planet. They're sort of platy, and the spacecraft took some measurements of the chemistry of these rocks and determined their composition. And their composition is a rock type called basalt. And I want to tell you about basalt. So I have this little basalt montage, but in case, so basalt is what comes out of the volcanoes of Hawaii. So this is the flow that happened a couple of years ago on the Big Island of Hawaii. It is the rock that's the dark plains of the moon, the mare of the moon. It is the surface of Mercury is dominantly this rock. The lava flows on Mars are the same rock. We have samples of those rocks from space, from Mars, that are the same rock type. And I got excited when I did this, but the surface of Io, which is a moon of Jupiter, is also basalt. And the point of all this is to say that anytime you have volcanism that melts the mantle, the interior directly, this is the rock type you get. And this is what we expect on Venus. And so we've explored Venus. The last 3 missions to go to Venus were a US mission, Magellan, a European mission, Venus Express, and currently the Japanese Space Agency has Akatsuki. And so I'll just spend a few minutes, because I see the time, just about 10 minutes, just telling you a little story about this planet. But the Magellan spacecraft put Venus into context, put the landing sites into context. So this is a map of the entire surface of Venus. And what you're seeing is topography or elevation. So the blue stuff is low and the red stuff is high. And remember, the surface of Venus is about the same size as the Earth. So if you can sort of, envision in your mind like a map of the world, of the Earth, with North America over here and South America and Asia and Africa. I mean, this is the scale of what we're seeing on Venus. And we can divide Venus into roughly 3 different types of terrains. Most of the surface of Venus is just lava flows, just volcanic lava flows. There's an area here that has sort of bigger volcanoes, and then an area, a couple of places on Venus, about 10% of the planet, that's made up of a rock, a terrain we don't have on Earth, called tessera terrain. And I'll show you a picture of it. These are radar images of these surfaces. So the color here is relates to roughness. So the volcanic plains are smooth and dark, and anything that's rough at the centimeter scale is bright. And so this tessera is really faulted and folded and deformed. And then we have volcanic lava flows, and also some volcanoes together, larger volcanic features. I'm just gonna skip a little bit to say, one of the things, actually, I'll go back. I'm sorry. I'll go back here. So one of the things that we can see from looking at these relationships is that anytime we have the tessera and the plains in contact, the tessera are always older than the plains. And so there's sort of a change in how Venus worked, where whatever made the tessera was occurring, and then later lots of volcanoes erupted. And we can actually tell the sort of general age of the surface of Venus the same way we do for any planet, which is by counting craters. So this is a map of all the craters on Venus, and this is a comparable map of all the craters on the moon. And the more craters you have, the older a surface is. So if we count up the number of craters on Venus, we can see that the surface of Venus is relatively young from a geologist's perspective. It's only about 500 million years. So I'm going to show this to you in terms of of Earth history, and then we'll talk. We'll have a couple. Then we'll sort of wrap things up. But this is so this is a stratigraphic column for the Earth. And I sort of flipped it on its side, but This is today, and this is 4.6 billion years ago when the Earth formed and all the planets. And so we divide up the Earth eras into, into different eras and eons, and they're mostly based on fossil evidence. So most of the action on Earth that we're familiar with happened. Complex life started on Earth about 500 million years ago. Complex life, but the earliest evidence for life was quite early. About I think our earliest evidence for life now is about 4.2. So if we compare that to what we understand about Venus, Venus's history is very simple from what we understand so far. That the most recent stuff is volcanoes, and then a little bit older than that is this tessera terrain. And the average crater age is really young. We don't have any history that we in the plains that tell from the first 80% of the surface of Venus. And so because the tessera are the oldest stuff, we are really interested in them because they can tell us something about what was happening early in Venus's history. And that is, that's the time when life started evolving on Earth and persisted to present day. And these are just some pictures of what the surface of Venus looks like, just some other pictures of volcanoes and volcanic flows. And there's lots of volcanoes on Venus. If you like volcanoes, Venus is the place for you. So I'm going to, I'm just going to talk a little bit. I'm going to skip a little bit, okay, because of the time. But I want to just talk about the evidence that we have for water on Venus. And there's several lines of evidence, but I'm going to summarize. I'm going to summarize them by talking about about this. Just coming back to this stratigraphic column. So we can look at the atmosphere of Venus today and look at the ratio. It's basically the isotopes of hydrogen in the atmosphere of Venus. And that tells us something about the amount of water that has been present on Venus and how much was lost. And so the chemistry of Venus tells us that Venus has lost a lot of water over its history. But the question has always been how much and how long did it take to lose that water? And so we there's new data that show over the new data have come out in the last couple of years that show that Venus should have started with an ocean, and then that ocean may have persisted on Venus for a couple billion years. And this is really new, a new modeling based on the global climate models that we use for Earth. But to put this in stratigraphic context, that would mean that when life developed on Earth, Venus had water. And when life started to develop photosynthesis, Venus had water, an ocean. And when life started to diversify and form different types of oxygen started to grow in the Earth's atmosphere, Venus had an ocean. And so this, a better understanding of the presence of water on Venus and the longevity of water on Venus suggests that Venus was habitable for a long period of time. To contrast, Mars was probably oceanic maybe for the first billion years or so, but it looks like Venus could have been oceanic for a long period of time. And if that's the case, the oldest rocks on Venus are in this complex tessera terrain, and that's where we want to look. So I'm going to actually, I'm going to back out for a second and then back in. Okay. So just hold on a second because I wanted to keep this. I can't see my mouse. Hold on. Sorry, everybody. I wanted to keep this to about half an hour. But
so I'm just going to skip over a couple things and go to sort of the last couple of slides. Okay, so I'm going to reshare, and here we go. Okay. So this is another way to look at the history of the 4 inner planets in the solar system. So what you're seeing here is Mercury, Venus, Earth, and Mars. This is at the time of the origin of the planet, and this is today. And for each one of these planets, this paper is showing in red the length, the time over which the planet was tectonically and volcanically active in red. And we see that Mercury cooled off fast. So volcanism was early. Mars cooled off a little slower, but Earth is volcanically active, and so is Venus. So this is a criterion for habitability. And then the blue is the lifetime of oceans on the planet. And so we know that Earth had oceans very early in its history, and they persist today. We see evidence on Mars of an ocean early in its history. But our new understanding of Venus is that it had an ocean at the beginning, like Earth, that may have persisted for a long period of time, and the time over which life evolved on the Earth. So this is a primary reason why we think that Venus may have been habitable. And it turns out as well that even so, the data that I just showed you suggests that Venus may have been habitable in its early history, but it also may be inhabited today. And this is actually a very old idea. So Morowitz and Sagan wrote a paper in 1967 called Life in the Clouds of Venus. And what they realized is that if you go up into the clouds, the temperatures get cooler. And the cloud deck of Venus is actually kind of shirt sleeve weather. It's kind of, it's not that hot. And so there are actually creatures that live in the atmosphere, clouds of Earth, or at least spend some of their life cycle on Earth. And we can look at the particles in the clouds and see that there's lots of sulfur and iron and other elements that are tasty things to eat for microbes. So they suggested that life might be in the Venus clouds. And this is something that hypothesis was actually rejuvenated recently by the detection of a biomolecule, a phosphine, PH3, in the clouds of Venus last year. So there's some suggestion, enough of a suggestion that we need to look at the Venus clouds as a site where life might exist on Venus today. And why this is all really exciting too is because, so we are at a time in our history where there are so many planets that we're discovering, and a lot of these planets are Earth-sized. So here's our solar system to scale: Mercury, Venus, Earth, Mars. This is the solar system around the planet, the sun, TRAPPIST-1. And there are, 7 planets that have been discovered so far. And their sizes, all the sizes here are to scale. So there are a ton of Earth-sized planets in this system, this extrasolar system. And these planets are also Venus size. So we want to know, as we find more and more Earth-like planets across the Earth-sized planets across the galaxy, if they're like Earth or like Venus or something else entirely. So one of the ways that we like to think about Venus is that it's the only other Earth-sized planet that we will ever be able to touch, really, to visit. We will never be able to send a spacecraft to these planets in other solar systems. They're just too far away. But we have an example of an Earth-sized planet, the closest planet to us, Venus, which can help us understand how, what the different fates of Earth-sized worlds can be. How do we take 2 planets that are made of the same stuff, have live the same length of time, and one evolves to be like Earth and one evolves to be like Venus? So that's why we need to send a mission
And this is just showing that this is solar temperature versus distance of many of the exosolar planets that we've been discovering, and many of them are close to their star, like Venus, and Venus may be a better analog for them. So I'm going to just end by talking. I'm just going to talk a little tiny bit of politics, and then we'll end. Just 2 more slides. But I do want to say that this is a beautiful image that the NASA administrator shows a lot of the spacecraft that are in orbit around our solar system. This is the NASA science fleet. So what it's showing is all the spacecraft, the NASA spacecraft around the Earth and the Moon and Mars, and there's Voyager 1 and 2, and then galactic stuff and solar stuff. And then if you look at Venus, there's nobody around Venus from NASA. And so this is a timeline of the missions that have gone to Venus. And just so the last US mission so this is time along the bottom. The last US mission to Venus was the Magellan mission in the 90s. And then we've had these 2 international missions. And so we are at the cusp here of there are a slew of missions that have been proposed to study Venus from both the US and Indian Space Agency, the Russian Space Agency, the European Space Agency. And the 2 that are in contention right now are the Veritas orbiter and the Da Vinci probe. And we have been working on these for years. And we expect to hear whether one of them will be selected for flight within the next month, actually, hopefully early June, to know whether one or both of these is selected to go to Venus. So it's been a long time since the US has been to Venus, and I really hope that that we get a chance to go in the next couple of years. So with that, I will end this talk.